Good morning, everybody. Today is 22nd December 2020, and the day is Tuesday. My name is Ferhan Mazher, and right now I am in the 10 Cambridge class. The subject we are studying is Physics 5054, and we are working on a chapter. The name of the chapter is Electrostatics. We also call it Static Electricity, and we are almost at the end of this chapter. I think it will require only two more lessons, and this will be 100% completed. One very important thing about this chapter, the topic which we want to do today from this chapter, when we talk about two forces, for example, when I say we have two charges, for example, I say if the charges are same, they will be repelling each other. If the charges are not same, they will be attracting each other. We say that the like charges repel each other, on the unlike charges attract each other. The positive and the positive, they will be attracting each other, and the negative will be repelling each other. Positive will be repelling each other. Positive and negative, they will be attracting each other. So whenever you bring two charged bodies close to each other, what happens? They have very strong force of attraction or very strong force of repulsion. So the one thing which in the next 5 minutes I'm going to tell you, that is not included in your syllabus. Actually, the equation is not included in your syllabus, but the concept is included. You see, I can actually calculate. This is not in your syllabus, but it will take just 5 minutes. I can actually calculate the force of attraction or force of repulsion between the two charged bodies. Whether that is attractive force or it is a repulsive force, we can actually calculate. So the force of attraction between two charged bodies or force of repulsion between two charged bodies, that force of attraction or force of attraction, repulsion, whatever that force is, we call it electrostatic force of attraction, or we call it electrostatic force of repulsion, and that can be calculated. And we have a law, we call it Coulomb's law. Coulomb's law says that, for example, let me show you on your screen that, for example, if I have, you can see these two, here I have two charged bodies. Let me increase the size so I can. For example, here I have two charged bodies. On your screen, I think that you can see that. Two charged bodies. The charge on the one body is Q1 and the charge on the other body is Q2. And the distance between the centers of these charged bodies is R. So in this case, one is positive, the other one is negative, so there will be force of attraction. This electrostatic force of attraction between the two charged bodies, the Coulomb's law says that it depends upon two things. This force of attraction or force of repulsion between the two charged bodies depend upon two things. One, the force of attraction, the electrostatic force of attraction is directly proportional to the product of the charges on both these bodies. The force of attraction or force of repulsion is directly proportional to the product of the charges on both the bodies. It means F is directly proportional to Q1 multiply Q2. And the second statement is that the force of attraction or force of repulsion, electrostatic force of attraction or electrostatic force of repulsion, that force is inversely proportional to the square of the distance between their centers.
सर ये हमारे
So
सिलेबस में है.
the equation is not in your syllabus, but the
Okay, sir.
concept is in your syllabus.
Okay.
Okay. So it means the larger the amount of charge on the bodies, the stronger will the force of attraction or force of repulsion. The more the charge on them, the more the force between them. Less the charge on them, there will be less amount of force of attraction or force of repulsion. And with the distance, the relationship is opposite. If the distance between the charged bodies, you increase the distance, the force of attraction or force of repulsion will decrease. If you decrease the distance between the charged bodies, the force of attraction will increase. If the charged bodies are close to each other, the force will be stronger. If the charged bodies move away from each other, the force between them will become weaker. The F is inversely proportional to the square of the distance between their centers. Okay, so let me show you that equation actually with the final equation mathematically which we get. That is, the equation is not in your syllabus, but the concept is in your syllabus. You see this F, this force of attraction or force of repulsion, whatever that force is directly proportional to the product. Product means multiply. Is directly proportional to the product of the Q1 and Q2 and is inversely proportional. That's why you see the R is downstairs. And is inversely proportional to the square of the distance between their centers. And when you join these two things together and you remove the sign of proportionality which you have learned in your mathematics, when I remove the sign of proportionality, chapter number 2, D2, where you have learned about the proportions, when we remove the sign of proportionality, we introduce a constant there. We put an equal sign and then we put a constant there. In this equation, the constant is K. The constant is K. And let me show you the whole thing now. Okay. We know that a force of attraction or repulsion acts between two charged bodies. How is this force affected when the magnitude of the charge on the two bodies or the distance between them is changed? In order to find the answer of these questions, a French scientist, Charles Coulomb, in 1785 experimentally established the fundamental law of electric force between two stationary charged particles. Coulomb's law says the force of attraction or repulsion between 2-point charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. Therefore, these equations have been, I don't know when I downloaded it, something went wrong. So combining these equations, F is equals to K Q1 Q2 by R square. Equation number 13.3 is known as Coulomb's law, where F is the force between the two charges and is called the Coulomb force. Q1 and Q2 are the magnitudes of the two charges and R is the distance between the two charges. Figure 13.10 and K is the constant of proportionality. The value of the K depends upon the medium between the two charges. If the medium between the two charges is air, then the value of the K in SI units will be you will use this K value when you will be in your A levels. But just remember this number: 9 expo 9 Newton meter square per Coulomb square. Coulomb law is true only for point charges whose sizes are very small as compared to the distance between them. So here we have an example also. You see, in your exam, they will never ask you to use this equation. They will never ask you to actually calculate using this formula. So you don't worry. Only you should know that the force of attraction due to the charges, that depends upon the amount of charges in both the bodies. More the charge, the more will be the force, and is inversely proportional to the square of the distance between them. It means, what does this mean? In your exam, what kind of question they will ask you? For example, if I have two charged bodies and force of attraction between them, for example, is 20, and then you double the distance between them. So what will be the new force? When they were at a certain distance, the force of repulsion between charged bodies was 20 Newton. So now you doubled the distance between their centers. So what will happen with the force? We know that according to Coulomb's law, the force is inversely proportional to the square of the distance. So you doubled the distance. So it means 1 by 2 square, it means 1 by 4. So the force between them will become 1/4. It will become 20 divided by 4. It will be the new force between them. Or now the force of attraction or force of repulsion, that will be only 5 Newton. Okay? 5 Newton. So this kind of questions come, you don't actually have to do the calculation by using this Coulomb's law. Okay?
Yes, sir.
So another very important thing is the electric field and electric field intensity. So try to understand what I'm saying. For example, here I have a positive charge. Okay. So you can see this diagram on your screen. Let me increase the size and bring it in front. You see, here I have this diagram. So in this diagram, you can see that I have here I have a Q positive charge. So this Q positive charge, around this, we have a certain area. Around this, I have a certain area around this. In that area, in that space, in that region, if I will bring another charge, that charge will experience electrostatic force. That charge will experience a force of attraction or a force of repulsion. You see, this Q charge, around this Q charge, I have a certain space, certain area, certain region. In that region, if you place another charge, that charge will definitely experience a force of attraction, or it might experience a force of repulsion. It will experience a electrostatic force of attraction, or it will experience electrostatic force of repulsion. If you go outside that area, if you place another charge outside that area, there will be no force of attraction or force of repulsion between this positive Q charge and that charge. So it means that around a charge, there is a certain area. If you put another charge in that area, that charge will experience a force. And if that charge is outside that area, it will experience no force of attraction or repulsion due to this charge. So that area, that space, that region around that charged positive Q, that is known as its electric field. So around a charged body, let me show you. This is a very important thing. For example, suppose okay, let me take out the paint. Okay, suppose here we have this area, and I have a charged body here, and suppose it's positively charged. Suppose it's a positive charge. Okay. So, and its value is Q. So around that charge, I have this area, this boundary. If I will bring another charge, for example here, if I will bring another charge here, it will feel, because both of them now are positive. So see, it will experience a force of repulsion. So this will go in this direction. Okay. But if you put a charge outside that area, for example, if I put a charge outside this area, this charge will experience no force due to the Q charge. So around a charged body, there is a certain area, there is a certain region, there is a certain space. It's kind of boundary around a charged body. If you come inside that charged body, if you come inside that area, you will experience a force of attraction or your force of repulsion. If you are outside that area, you will experience no force of attraction or force of repulsion due to this charge. So this area, this space around that charged body is known as the electric field of that charged body. So you understand this idea? Electric field. Hello?
Yes, sir. Yes, sir.
Okay.
Yes,
Okay.
sir.
So, very good. So let's go back to that book. So, okay, now when you place a test charge, you know the test charge means its charge is 1 coulomb, and in whatever direction it will move. If you place a test charge, I'm using the word test charge. Test charge means it's a 1 coulomb positive charge. If you place a test charge inside the electric field of a charged body, so whatever will be the force and whatever will be the direction of the force, the force that will be known as the electric intensity, or you call it the electric field strength at that point, and whatever will be the direction of that force, That will be the direction of the electric field there. Try to understand this thing. For example, for example, these are the okay. For example, I put a positive test charge here. It's a positive test charge. It means it's the charge on this body, this blue body is 1 coulomb. So now you see what will happen. It will experience a force of repulsion. This is positive, this is positive. So here it will experience a force of repulsion. So this will be the direction of the force. So it means at this point where you have placed the test charge, at this point, the direction of the electric field is in this direction. Wherever that force is, whatever is the direction of that force. And if you want to find out the electric field strength, whatever is the force experienced by that unit positive test charge, that is known as the electric field strength. Okay, for example, I place a test charge in this place. Sorry. For example, I place a test charge here. Very close. It's a test charge and it is positive. It has unit charge on it, it's positive. It's positive. So it will experience a force in this direction. So the electric field, the direction of the electric field is whatever is the direction of the force, the direction of the electric field here at that point is the direction of the force, whatever is the direction of the force here on this blue color positive charge, positive test charge. It's a unit charge, which means it has 1 coulomb charge on it. And whatever is the force experienced by this unit positive test charge, that is the electric field strength at that point. So I'm telling you two things: to find out the direction of the electric field and to tell the direction of the electric field. Do you understand this idea?
सर लास्ट बात नहीं समझ आई.
So what you have understood, just tell me that.
कि सर जब इलेक्ट्रिक फील्ड से बाहर कोई चार्ज होता है तो वो एक्सपीरियंस नहीं करता फोर्स, लेकिन जब उसके अंदर होता है तो वो
Yeah.
एक्सपीरियंस करता है फोर्स. और आपने ये भी बताया कि जितना करीब होगा चार्ज की उतनी ज्यादा फोर्स होगी, मतलब उतना ज्यादा
Okay.
इलेक्ट्रिक फील्ड की स्ट्रेंथ होगी. ये बस समझ आइए.
Okay. Okay. Anybody else? Anybody else would like to say something? What you have understood right now? Okay. Okay. That's good. According to Coulomb's law, if a unit positive charge Q naught, call it a test charge, is brought near a charge Q, call it a field charge, placed in a sphere, in space, the charge Q naught will experience a force. The value of this force depends upon the distance between the two charges. If the charge Q naught is moved away from Q, this force would decrease till at a certain distance, the force would be practically reduced to zero. The charge Q naught is then out of the influence of the charge Q. The region of space surrounding the charge Q in which it exerts a force on charge Q naught is known as electric field of that charge Q. Thus, the electric field of a charge is defined as the electric field is a region around a charge in which it exerts electrostatic force on another charges. The next thing is the electric field intensity. The strength of an electric field at any point is known as electric field intensity. In order to find the value of the electric intensity at a point in the field of the charge positive Q, we place a test charge Q naught at that point. If F is the force acting on the test charge Q naught, the electric field intensity would be given by the formula E is equals to F by Q naught. The electric field intensity at any point is defined as the force acting on a unit positive charge placed at that point. The SI unit of electric intensity is newtons per coulomb. If the electric field due to a given arrangement of charges is known at some point, the force on any particle with the charge Q placed at that point can be calculated by using the formula F is equals to QE. Electric intensity being a force is a vector quantity. Its direction is the same as that of the force acting on the positive test charge. If the test charge is free to move, it will always move in the direction of the electric intensity. Okay. Let me do the last time one more thing. Let me take out the new one. Okay. So for example, you have a Q charge which is positive. This one is positive. Okay. Its name is what? Q. And around this we have area. Around this we have area. Around this I have this space. You know this boundary, I'm trying to explain it again, okay? So around this charge Q, which is a positive charge, I have this area, this boundary, which is known as this electric field. If another charge, let me say it's a test charge, it is also positive. If another charge will be outside this field, this boundary, this charge will experience no force of attraction or force of repulsion. But if this is inside, for example, it comes here. If you place it here inside, if it comes inside that boundary, it will definitely experience electrostatic force. So at this point, in the electric field, inside the electric field, if you put a positive test charge, which is a unit charge, means the value is 1 coulomb. So when you place, wherever you place a positive test charge inside the electric field, so this will experience a force. So the force experienced at this point by this unit positive test charge So this test charge will move in this direction, in the direction of the force. So whatever is the direction of the force, same is the direction of the electric field there. Same is the direction of electric field there. And the intensity of the electric field can be calculated by the formula, the force experienced divided by the amount of this charge, the test charge, U0. Okay? So if you know the electric field intensity and you know the amount of charge, this body's charge, and you know the electric field intensity here, you can very easily by this formula calculate the force of attraction, force experienced. You don't have to go into the formula. Don't worry about it. You just know the idea. That's it. Now what you say? Do you understand this thing? Now can anybody tell me what is the electric field intensity and what is the direction of the electric field at any point inside the electric field? Can anybody tell me? Anyone? Can anybody tell what is electric field? How you find the direction of the electric field? Hello? Dua, are you listening?
सर डायरेक्शन ऑफ इलेक्ट्रिक वो होती है जो डायरेक्शन ऑफ फोर्स होती है, वही डायरेक्शन ऑफ इलेक्ट्रिक फील्ड होती है.
Yes. But there is a condition. The charge which you will put inside the electric field, that should be a unit positive charge. We call it test charge. That is must.
Okay, sir.
To test the direction, you will put a unit positive test charge. So in whatever direction,
रखेंगे.
yes, the test charge must be a unit positive charge. So whatever will be the direction of the force, that will be the direction of the electric field there. And the force experienced, if the magnitude of the force experienced, you know that, and you divide it with the Q naught, you will get the electric field intensity. And I am saying that don't go into the formulas. We don't need in O levels the formulas, but the idea you should understand. So in this, the region, you know, that black boundary around that positive Q charge, that is known as its electric field. So if you go outside this field, you will experience no force of attraction, force of repulsion with any other charge due to the Q. If you come inside this, you will experience force of attraction or repulsion between. So let me go to the next thing. This is very important, you know. Whenever, whenever you bring, you have heard this word, whenever you bring you see this diagram, sometimes this diagram comes in paper. If you have a positive charge, if you have a positive charge, these here I have shown lines. These are imaginary lines. These lines are coming out of the positive charge. So whenever you will have a positive charge, the positive charge, these are imaginary lines. These are not actually there, but these are imaginary lines. And from the positive charge, they always radiate. They come out. They fan out. They are radiating. They are kind of coming out. So from the positive charge, there are imaginary lines which we use to explain its behavior. These imaginary lines are known as electric field lines. And from the positive charge, they always come out. These imaginary lines are known as electric field lines. Here you see on your screen, these are negative line. I have a negative charge here. And you can see that these are imaginary lines and they go into the negative charge. These imaginary lines around a charged body, they are known as electric field lines, or we call them electric lines of force. Electric field lines, electric field lines, electric force lines. So if you have a negative charge, they will be going into that negative charge. And if you have a positive charge, they will be coming out of that positive charge. These imaginary lines, why I draw them? Why we draw them in physics? They are not there, but we imagine them that they are there. Because by using these imaginary lines, we are able to describe or explain the behavior of the charged bodies when they are around each other. For example, if you bring two charged bodies close to each other, they start attracting each other. Or they might start repelling each other. To explain this behavior, these imaginary lines are very useful. That's why this is happening. So these lines, have a look at them and don't forget them. These imaginary lines around a charged body, they are known as electric field lines. And from the positive charge, they always come out. And in the negative charge, they always go in. And wherever these lines, with the help of these lines, I can also describe the electric field intensity. If in a place the electric field lines are close to each other, the distance between the two lines is smaller. Wherever the electric field lines are concentrated, in that region, the electric field is strong. Where the electric field lines are away from each other, wherever the distance between the electric field lines is larger, the electric field intensity or the strength of the electric field there will become weaker. So if you find two regions, in one region, the electric field lines are very close to each other, that means the electric field is very strong there. And if the distance between the electric fields is larger, if the electric field lines are away from each other, it means the electric field is weaker. For example, if you are near this charge, you will see that the electric field lines are close to each other. So it means the near the charge, the electric field intensity will be stronger. But if you move away, so for example, here, if you move away from the charge, you will see the distance between the electric field lines has become larger. So the electric field here will be weaker. So from the positive, the electric field lines are coming out, and from in the negative, the electric field lines are going in. Now, let me show you another diagram. We make these imaginary lines to explain the behavior of the charged bodies when they are close to each other. Let me show you this diagram. You see here, with the help of the electric field lines, we can explain that why a positive and a negative will be attracting each other. You see, when you bring two charged bodies, one is positive, the other one is negative, in front of each other, close to each other. So the electric field lines which are coming from this positive, they will be radiating out. They will start going into this negative. So the electric field here, the electric field lines which are coming from this positive, they will start going into this negative. So in the middle, you can see the electric field has become very strong. Here, the electric field lines are very close. So here, the electric field is very strong. And here, the electric field is weaker. So you see, with the help of these lines, I can explain a little bit that why a positive and negative will be attracting each other. Because the lines of electric field lines coming out of the positive, they are directly going into the negative. So they will be attracting each other. In the same way, let me show you here. Here you can see, I bring a positive and a positive charge in front of each other. So from the left positive, the electric lines are coming out. From the right positive, the electric lines are coming out. So from both of them, the electric lines are coming out. So you see, there is a property of electric field lines that they do not intersect each other. Remember this property of electric field lines, that they do not intersect each other. So when they do not intersect each other, what will happen? So the electric field lines coming from this positive, electric field lines coming from this this charge, they cannot intersect each other. So they will move away from each other. So here a gap will be created. So here there is no electric field lines. So basically what happened? This is how the positive will be repelling each other, because their electric field lines cannot intersect each other. So this is also giving out electric field line. This is also giving out electric field line, and they do not intersect each other. So that's why the positive and positive will be repelling. In the same way, if you bring a negative and a negative in front of each other, so both the negatives, the electric field lines are going into them. In the negative charge, if you have a negative charge, the electric field lines always goes into the negative charge. So both of them are negative. So the electric field lines are going into them, in both of them. So the electric field lines are going into both of them. So you see, and there is a property of the electric field lines that they do not intersect each other. They do not cross each other. They do not intersect each other. So what will happen? The electric field lines going into here, the electric field lines going into here. So here we will have a gap. So this negative and negative will be repelling each other. So this diagram is very, very, very important. Okay. I just showed you these three diagrams. You will find these diagrams also in your own book, Physics Matter. Okay. So he says, electric field lines. The direction of the electric field intensity in an electric field can also be represented by drawing lines. These are imaginary lines. These lines are known as electric lines of force. These lines are introduced by Michael Faraday. The field lines are imaginary. They are imaginary lines around a field charge with an arrowhead indicating the direction of force. Field lines are always directed from positive charge towards negative charge. The spacing between the field lines show the strength of electric field. Okay. So that's it. Uh, that's it for today. I think that I hope that this is helpful to you. So we will continue this. We are working on the electrostatic electricity, or we call it the static electricity. We are working on this chapter. We are almost about to finish this chapter. Today we have talked about the electric field. We have learned what is the electric field. We have learned what is the electric field intensity. We have also learned the formula for the electric field intensity, which is not in your syllabus, but the ideas are in your syllabus. And then we have learned about electric field lines. These are imaginary lines. From the positive charge they are coming out, in the negative charge they are going in, and how we draw these electric field lines pattern when a positive face each other, when a positive and a negative face each other, and when a negative face each other. And also in the start of this chapter, I have explained to you the Coulomb's law. Uh, the name Coulomb's law is not in your syllabus. Its mathematical equation is also not in your syllabus. But in your syllabus, they will ask you question that if I increase the distance, the force of attraction or force of repulsion will decrease or increase. You see, the mathematical formula is not in your syllabus. The name Coulomb's law is also not in your syllabus. But its explanation about the magnitude of the force of attraction or repulsion when you change the distance, that is in your syllabus. So you read it, the whole thing, and it will be good. So I hope that this lesson has been a little fruitful to you. You see, the ideas are little weird because we are talking about a word which is totally imaginary, but it's real. It's not actually imaginary, but you have not seen it. So I hope that this thing is clear to you. So have a good day. Thank you very much, everybody, and God bless you all.